There are other regression methods besides least squares. For instance, for least squares, what we do is we compute residuals from our model, and then we choose the parameters which will minimize the sum of the squared residuals. Essentially, we're treating the squared residual as a penalty, and we choose the parameters to minimize the penalty. But we could choose other penalty functions instead. In general, we do have a few basic requirements. We require that the penalty is not negative. We do not reward mismatch between model and data. We also generally require that a bigger residual does not decrease the penalty. We don't reward residuals getting bigger. But beyond that, we have a great deal of freedom in how to choose our penalty function. For example, instead of minimizing the squares of the residuals, we could minimize the sum of the absolute values of the residuals. Sometimes this is called least absolute deviation regression, sometimes called L1 regression. And it does have this advantage. Sometimes there's an extreme outlier in our data. In fact, often that happens because it's just plain an error. An extreme outlier gets an extreme deviation, a very large residual, and when we square what's very large, it gets very, very, very large. It can get so large that it'll overwhelm least squares regression, and that one single data point can throw off the regression. However, when we use the absolute value penalty instead of the squared penalty, we mute the impact of any single very large value. That means that L1 regression is much more resistant to outliers, and that's a property which makes it what is called robust regression. There are other possible penalty functions we could use. Another strategy, for instance, is to let the penalty be the squared residual up to a point, but beyond that point, instead of growing as the square of the residual, the penalty only grows linearly. It's a process called Windsorizing. There's another strategy called Tukey's byweight, in which the penalty grows as the residual gets bigger up to a point beyond which it doesn't grow at all. These other penalty functions are chosen to prevent outliers from having too much effect. In other words, they're chosen to make regression robust. Here are some examples of the penalty functions that are used for these different forms of regression. This is just a quadratic curve. This is the least squares method, where the penalty function is the square of the residual. Here's the least absolute deviation, or L1 regression penalty function, where the penalty is simply the absolute value of the residual. Here it is with Windsorizing, where it grows quadratically up to a point, but beyond that point it just follows a straight line. So it's kind of a in-between between least squares and least absolute value. Here is Tukey's byweight, where the penalty grows as the residual increases up to a point, but beyond a point the penalty is big, but it doesn't get any bigger. Now, those aren't the only ways to do robust regression. There are even methods which are called non-parametric, but since some of them are designed to estimate parameters, in fact, that's kind of the point of regression, maybe a better name for them would be distribution-free. A good one for fitting a straight line to data is something called Thiel-Sen regression. If we take any two data points, we can compute a straight line between them. If the data points are x sub j and x sub k, occurring at times t sub j and t sub k, the slope of that line is just the ratio between the data difference and the time difference. We can also compute the median time of all the time values and use it to compute the intercept of that line at the median time, which is given by this formula. Now, we will end up with a very large number of slopes, a slope for each pair of points, and intercepts, an intercept for each pair of points, because each pair of points defines a straight line. So we'll end up, in most cases, with far more estimated slopes and intercepts than we have actual data values. That's fine. The final thing we're going to do is we're going to compute these estimates for every possible pair of data points, which gives us a very large number of them. The Thiel-Sen estimate is the median of these, not the mean, but the median. The median slope is our estimate of the regression slope. The median intercept is our estimate of the intercept at the median time. We can even compute a confidence interval for the Thiel slope. For large enough samples, we can compute a confidence interval at 1 minus alpha confidence by using the normal distribution approximation. We retrieve the standard normal z-value for the desired confidence level. For example, for 95% confidence, it's 1.96. Then we compute this quantity where n is the number of estimates we have, not the number of data points we have. We'll generally have more estimates of slopes and intercepts than we have data points. Lastly, we compute an upper and lower index values. We have a lot of estimates for the slope. We will arrange them into sorted order from lowest to highest. The lower index value will be this, where the d is the quantity we just computed previously. The upper index value will be this. We'll round L to the nearest lower integer, round U to the nearest higher integer, and then we'll take those as the index values in the sorted list of which slope estimates to choose as the limits of our confidence interval. Here, for example, is an example case of something where robust regression is probably a good idea. These data consist of a straight line trend, a perfectly straight line, plus random noise. And if you look up this stuff at the top, you can probably see that it is ever so slightly and gently increasing as time goes by. So there's that increasing trend shown by the actual true trend. However, there's this one data point down here, which is definitely an outlier. It's way down there. In this particular case, it's just a mistake. Somebody wrote down the wrong number, or maybe the decimal point got transposed. In any case, it ain't right, and it might throw off our regression. The true trend is trending upward ever so slightly, but if we compute a trend by least squares, it will seem to be trending downward. So here's a case where this extremely large residual got squared, which made it extremely, extremely large, large enough to throw off least squares regression and give an apparently negative downward slope when the real slope is positive upward. If we use a robust method like Thiel-Sen regression, then that single outlier will have practically no effect. It'll be the bulk of data points which determines the regression line, and we'll see that we actually get a very good fit. In fact, the slope of this Thiel-Sen regression line is very close to the true slope of the trend on which the data are based. So by using robust regression, we are able to mute the presence of outliers, especially extreme ones, and prevent them from ruining our regression and giving us what is essentially a nonsense result.